Good afternoon. My name is Cristina Charlton-Perez. I am the Editor-in-Chief of Meteorological Applications. As with all the journals in the portfolio of the Royal Meteorological Society, there are two editors-in-chief for each journal, and my partner editor-in-chief is Professor Dino Zardi. We have a large group of associate editors from all over the world at the journal, with a wide variety of research expertise and interests. The METAPS editorial board works together as a team to ensure that the journal runs smoothly and that we continuously publish excellent science and technology that is of interest and use to our readers. Today, it is my great pleasure to welcome you to the very first Meet the Author webinar. It is the aim of this webinar to connect our readers to our authors and also to demystify the process of publication if we can. We have managed to secure two of our recently published authors to join us and tell us informally about their papers. They will talk for about 15 minutes each, and then we will open the floor for questions after each of their talks. On this platform, you will be unable to turn on your camera or microphone to ask the questions. So you should type your questions as they come up on the chat function at the side of your screen. Questions should only be based on the scientific content being presented or about the publication process. I will read the questions aloud to the authors so that they can answer them. So we've chosen these two papers and these authors for multiple reasons, including the applications of meteorological science in these papers are clearly laid out, as well as the benefits to users of the forecasts. We also thought it was a nice pairing of these two papers to have a flood forecasting and a drought forecasting paper. So one paper about too much rain, another paper about too little rain. Finally, we wanted to showcase the international scope of the papers that are published in METAPS. International collaborations across different institutions are evident from both papers. The first one includes authors from the UK, the Netherlands, and Australia. And the second paper, authors from the UK and from various institutions in Kenya. Just to tell you a little bit more about Meteorological Applications, we're a fully open access journal, online only. Open access waivers are available through various arrangements. And society members are also eligible for discounts for publication if they are the corresponding author. We currently have two calls for papers for two special issues, which are the impact of the present pandemic, a feedback loop between climate, air pollution, and the COVID-19 outbreaks. And the next special issue that we've just introduced is on atmospheric processes and applications in urban, coastal, and mountainous terrains. We have some other special issues in the pipeline for next year, so please stay tuned. And maybe your research area will come up and you'll want to publish with us. Just a few tips on the web browser Demio. Demio is best used on platforms, browsers such as Chrome, Firefox, Safari, and Edge. Now, to make the slides larger when they appear, you need to use the two arrows pointing at opposite ends of the square. To close the chat to make things even larger, you use the arrow that comes towards the vertical bar. And questions for the speakers can be posted on the chat at any time during the presentation, as you won't be able to turn on your camera or use the microphone to interrupt. So the questions, again, should be relevant to the presentation or to issues about publication in METAPS. Now, there may not be time during this webinar to answer all your questions, but we will take note of those questions. And over the next week, if you think of more questions, you can email conferences@rmets.org for the next week, questions about publication, inquiries about the papers, and we will try to get you an answer back as soon as possible. So now I'd like to present our first author. The first paper is Linking Weather Patterns to Regional Extreme Precipitation for highlighting potential flood events in medium to long-range forecasts. It will be presented by Mr. Robert Neal of the Met Office on behalf of all of his co-authors. His co-authors include Doug Richardson, Rutger Dankers, Ken Milne, Robert Cowling, Holly Clements, and Jonathan Millard. Rob works in verification, impact, and post-processing team at the Met Office. In this paper, Robert is working with data from numerical models covering a range of forecast lead times out to a month in advance. His personal main research interests include post-processing of ensemble forecasts, communication and presentation of probabilistic weather forecasts, and weather pattern forecasting applications for high-impact weather. Rob is also a musician who plays both the piano and church organ. He rings church bells as part of a band for church services and special occasions such as weddings, christenings, and national events. His paper that he'll present today was accepted on June 1st of this year. So now I'd like to turn over to Rob so he can continue and present his paper.
Thank you, Cristina, and good afternoon, everyone. In this talk, I will introduce you to the concept of weather patterns over the British Isles and how these relate very well to rainfall variability. This information can then be used within probabilistic medium to long range forecasts where weather patterns are predicted. The associated rainfall climatologies associated with the weather patterns can then be used to infer information on the expected rainfall totals. And as part of this research, we developed a forecasting tool for the Flood Forecasting Centre, which I will show you towards the end of my talk. Several people were involved in this research, and I'd particularly like to thank Doug Richardson, who led the write-up of this paper, and he's also published a number of other papers relating to weather patterns, some of which I will draw on in this talk. So a weather pattern in the context of this research can be defined as one of many circulation types over a defined region which differs in its characteristics from other weather patterns over the same region and can vary on a daily basis. And the picture here shows the set of 30 weather patterns that we used in this paper. So they were also published in METAPS back in 2016. And these weather patterns were derived through cluster analysis by clustering 154 years of daily mean sea level pressure data over Europe and the North Atlantic. And this process produced a set of 30 weather patterns, the ones that you see here. They're ordered from most likely to least likely, and the colours there show the pressure anomalies. So you can see the dark blues, they suggest negative pressure anomalies, so really deep areas of low pressure. And the reds are sort of indicating areas of high pressure where we have positive pressure anomalies. So the higher numbered patterns, they also tend to occur more in the winter months. And these are the more stormy types, and also the types that are most relevant to the rainfall that we're interested in this paper. The clustering also produces daily historical classifications, and this tells us which weather pattern was observed on each day during the clustering period. And this information is really useful because we can use it to calculate rainfall climatologies for each of the weather patterns. We can assign ensemble members to the closest matching weather pattern definition, and this allows us to produce a probabilistic forecast of weather patterns going out to the medium range, and we can even go out to the long range. So here I'm showing you an example forecast for the medium range period. So we're going out to 15 days here, and the darker the colour, the higher the probability. And these colours help us to pick out the most likely weather pattern transitions. So here in this example, we are likely to transition between weather pattern 21 to 29 and then to 30. And you can see that there's more uncertainty, as you'd expect, as the forecast lead time increases. These weather patterns are all variants of westerly or southwesterly cyclonic types. And the wind direction has a big influence on where the rainfall is likely to fall, and I'll show you a few examples of that later on. In this paper, we used rainfall observations from the Met Office Hadley Centre UK Precipitation Time Series called HAD-UKP. And this is regionally averaged rainfall, daily rainfall. And these regional averages are based on rain gauge data, so a handful of rain gauges in each region. So what we did is we calculated a rainfall climatology for each of these 9 regions over the British Isles for each day in the year. And we put a 101-day window around each day so that we could increase the sample size for each weather pattern, because some of the weather patterns, like weather pattern 30, which is a very stormy cyclonic westerly, that type occurs hardly at all in the summer. So we needed to make sure we increased that window so we could build up a decent climatology. And this box plot shows the rainfall distribution under weather pattern 21 for each of the 9 regions. And I've highlighted the wettest regions here under weather pattern 21, which unsurprisingly are southwest England, southwest Scotland, and northern Scotland. And for all regions, this weather pattern is wetter than average. So the average rainfall in each region is shown by the stars. A couple of years ago, Doug Richardson published a paper in the International Journal of Climatology, and he looked at how the rainfall climatologies compare between the Met Office weather patterns, which we use in this research, and the LAM weather types. So these plots show the interquartile range of daily rainfall for each region and pattern. So we're looking at the spread in rainfall in the middle 50% of the distribution. And what we can see is that intra-pattern precipitation variability is typically lower in the Met Office weather pattern classification compared to the LAM weather types. So this is telling us that the rainfall climatologies among the Met Office weather patterns in particular are different between weather patterns. So if we have the same rainfall climatology across all weather patterns, then our clustering has not done a very good job, but it's very encouraging to see that the climatologies and distributions do differ between weather patterns, so we can identify the wetter types. I'm now going to show you an example of a wet weather pattern and then a dry weather pattern, and we'll have a look at the climatological probabilities of exceeding different rainfall percentiles for each of these 2 weather patterns. So here I'm showing you a climatology map, a rainfall climatology map for weather pattern 21, which is this very cyclonic, very stormy southwesterly type. And the plot on the left shows the era 5 rainfall climatology for that pattern. So you can see it's very wet in the west of the British Isles. And then on the right, the plot on the right shows the climatological probabilities of exceeding a range of regional rainfall percentiles. This is for southwest Scotland. So if this was an average weather pattern in terms of rainfall, then you'd expect that curved line to go along the diagonal, but it's above the diagonal, so it means it's wetter than average. So to give an example, if you look at the probability of exceeding the 50th percentile rainfall climatology, then this weather pattern actually has an 86% probability under weather pattern 21. Then to look at a dry weather pattern, this is weather pattern 25, and we have high pressure centered just over Ireland there, dragging in a sort of a northwesterly flow over northern regions. So again, these empirical probabilities in the graph on the right are for southwest Scotland. And now the curved line is below the diagonal, suggesting it's drier than average in southwest Scotland. So to pick the 50th percentile line again, we can see that the 50th percentile regional rainfall value has a 10% probability under weather pattern 25. And what I thought was interesting also about this weather pattern was the very high probabilities of very low rainfall totals. So this is telling us that when we have this high pressure setup, although we have a lower probability of extreme severe rainfall, we actually have a high probability of very low value rainfall. Possibly this is drizzle, or this isn't the sort of weather pattern where you get big frontal systems rolling in. So it's going to be moisture coming in off the Atlantic and then causing drizzle or low amounts of rainfall up in Scotland. So we can take the information on the weather pattern forecasts, and we can take the climatologies, the rainfall climatologies, and merge the two together to produce a weather pattern forecasting application for rainfall, which we call Fluvial Decider, and this is used by the Flood Forecasting Centre. So in step one, we multiply the weather pattern forecast probabilities by their climatological probabilities of exceeding a number of rainfall centile thresholds, shown there. So the 99.7th centile is roughly equivalent to a once-a-year event. And then step two is to add together the resulting probabilities. So this results in an overall forecast probability of exceeding regional daily rainfall centile. And what's really nice about this is actually the end user doesn't, in theory, need to know anything about weather patterns, because all they're seeing is a probability of exceeding a rainfall threshold. Although I'd strongly argue that actually seeing the weather patterns associated with this is very powerful. It's good to be able to relate the rainfall to the large scale setup. And this is what Fluvial Decider looks like. This is how the Flood Forecasting Centre see it. It's used to provide guidance for their 30-day flood outlook. And it's presented in two ways. So the top panel shows it presented as a likelihood compared to normal, and the bottom panel shows it presented as probabilities. You see there's a horizontal line there, sorry, a vertical line there. The vertical line distinguishes between what was observed and what's being forecast. So anything to the right is what's being forecast. So in the bottom panel, where we've got a 30% probability at the beginning of a 1 in 10 day event, and in the top panel, that would equate to 3 times the normal likelihood. So the observed empirical risk shown in the left-hand side is then presented as an antecedent condition indicator, because if you've had a very wet period in the past and then it's forecast to be wet in the future, then you're more likely to see flooding. So in terms of best practice for this product, it's really designed to highlight periods at risk in week 2 and beyond, because obviously in week 1, forecasters have access to high resolution models and they can get much more detail from those. This is really just designed to provide an early heads up of what might be in the future. It's not designed for issuing warnings. It's designed for internal preparedness and for text-based forecasts, which convey levels of uncertainty in the medium range. And it's most suitable for capturing rainfall associated with large-scale frontal setups, mainly due to the observations that have been used in this. Long term, it might be quite nice to redo this with a gridded observation data set, and then we can present probabilities for each grid point over the British Isles. Okay, just in my last couple of slides, I thought it'd be nice to show you some of the verification around this. So this slide shows the verification of the underlying probabilistic weather pattern forecasts over nearly a 10-year period between 2010 and 2019. This is using the 51-member ECMWF ensemble. And we can see that there is better forecast skill in winter than summer. Predictability approaches climatology, so a skill score of around 0, by around 15 days. So, but in that period, we still have good skill, and actually quite a few of the patterns look like they would have skill beyond 15 days. And it seems like the westerly types have the best overall forecast skill, which is good because these are also the types that tend to bring us the most rainfall as well. And in the second of my 2 verification slides, this is work that was done and published earlier this year by Doug Richardson. And here he's actually compared the predictability of rainfall forecasts from our weather pattern approach, as demonstrated in Fluvial Decider. He's compared that predictability with that from, if you took rainfall direct from a dynamical model. So EPS WP on the left, that shows the skill score at a 16-day lead time if we use a fluvial decider type approach. EPSP, that is the skill score for each region if you take the rainfall direct from the model. And you can see that, they both compare quite well. And in some regions, the weather pattern-based approach actually has slightly better skill than from the direct from the model. And you can also see the skill if you use a Markov chain to forecast weather patterns, and then also the skill on the right if you have a perfect weather pattern forecast. So it's really demonstrating the power of this approach, assuming you have a good weather pattern forecast. Okay, so to summarize, forecasts of large-scale circulation can be used to infer details on rainfall variability. The top-level forecasting tool, which we call Decider, this provides the actual medium to long-range weather pattern forecasts. And then Fluvial Decider is our application of this. And this translates the weather pattern forecasts into rainfall forecasts, specifically for use by the Flood Forecasting Centre. And other applications may also be possible. So I'm currently working on some research, similar research over India to do a similar thing there. And we're also looking at relating things like lightning to weather patterns as well in some current research I'm doing. So thank you for listening, and I'll now pass back to Cristina.
Thank you, Rob, for that excellent presentation. We now have some questions appearing in the chat, which I'll read out to you. So we have a question from Nick, which is, I'll read out. Many thanks, Rob. Do you run this with any other models other than EPS at present?
That's a good question. We only run this off ensemble prediction systems at the moment, but we do use a range of ensemble prediction systems. So we use, as I've shown in this talk, we use the ECMWF 51 member ensemble, which goes out to 15 days, but we also use the 46-day version as well, the extended range version. We also assign the Met Office Global Ensemble to weather patterns and have a version of Fluvial Decider running off that. And we also, as a bit of an experiment, we're using Glossy 5 as well, going out to about 60 days. So what we have is we actually have a separate version of Fluvial Decider and Decider for lots of different ensemble prediction systems. And my long-term vision is to merge all these outputs together into a single multi-model ensemble. And I think that would be quite a nice, interesting bit of future research to verify a multi-model ensemble and see if it verifies any better than individual models on their own.
We have another question, this one from Alessandro, who asks, are there any issues related to climate change with Decider?
Well, the weather patterns were produced by clustering this 150-year period. So they are representative of the climate during that 150-year period. So I suppose you could argue that maybe, every few years we should redo this clustering. There's definitely a strong argument for doing that. But it's possibly not too important to worry about because we are forecasting these weather patterns. So the numerical weather prediction model, maybe it will predict more stormy types in the future, and that's fine because all that will happen is that these forecast scenarios will be assigned to the more stormy types in the future, and then maybe we'll get less forecasts for the more benign day-to-day types. And in fact, there is some research going on at the moment with James Pope at the Met Office, where he's looking at assigning climate projections out to 100 years in the future. He's assigning these projections to these weather patterns to see how the frequency of weather patterns might change in the future. And he's starting to get some really interesting results from that. So watch this space on that one.
That's a really good point, that you're using up-to-date numerical weather prediction forecast systems, and the ensemble ones, the ensemble prediction systems are very good. But with that underlying NWP model that has operational upgrades, so is continually updated and also with the data assimilation and the observations, that's all going in as well. It's not a climate model that's producing the raw output that you need. Is that right?
That's exactly right, yeah.
Fantastic. We have another question for you. This one from Amsala. Great talk. Can you explain, please, how each ensemble was generated?
There's a very large team at the Met Office, as there are in many other national Met centres and the ECMWF, that all run global ensembles. Large teams work on this. It's not an area that I work in, but essentially at a very basic level, they sample around an area of uncertainty because they know that there's errors in the initial starting conditions because there's observational errors. So there'll be sophisticated algorithms which randomly sample within an area of uncertainty, and then that will produce a range of different starting conditions which we can then use to initialize the model. So then the model will get run forward multiple times from lots of different starting conditions, and that will cause us to have different forecasts. So normally in the first few days, they might be quite similar, particularly at the synoptic scale. And then by the time you get into week 2 and beyond, there's normally quite a big divergence, as you saw in one of the slides that I presented towards the beginning.
Well, Rob, we have a few other questions. One from Pedro, who also enjoyed your talk. He asks, has this classification method been tried outside the UK? Is its application limited to mid-latitude regions?
That's a good question. I've tried it over a few regions of the world. I think it will work better over mid-latitudes where we have big frontal setups coming in, big areas of low pressure, big areas of high pressure. So I've just completed some work over India where I applied the same approach there. Obviously a very different climate to Europe, but it did work very well there because over India the weather can be classified quite nicely into different large-scale circulation types. So for example, we've got the monsoon onset, then the active monsoon, rake monsoon, and retreating monsoon. So I found the clustering algorithm was able to capture all those different types, and it was also able to capture variability within each of those types as well. So if we take the active monsoon, where it's very wet down the west coast of India and across central areas of India, then it found several variants within the active monsoon. So we were able to represent different spatial patterns of rainfall within the active monsoon. So it did work well there. And I've read papers as well where it's been done over Southeast Asia and parts of America as well. But it does tend to be in the mid-latitudes that it works best.
Are you planning on, just a follow-up question to that, are you planning on publishing your work on India?
Yes, in fact, that was published, I think it was late last year in the International Journal of Climatology.
Terrific, thank you. We have another question we have from Nikos. If I understood correctly, the verification is calculated based on ±1 day of observing the weather pattern. Did you check up to which day the performance of the NWP model exceeds the climatology, if the verification is performed without this 3-day temporal window?
Yes, I did. That's a good question. So my first version of verification didn't have any temporal windowing in it, and the predictability then was less. So I think the skill was somewhere between 10 and 15 days, whereas if you put the windowing in, then it extends out to at least 15 days for most weather patterns. And the reason I put the windowing in was because I felt that was a better representation of how the trained meteorologists use this forecasting tool. Because beyond 1 week, the meteorologists, they aren't writing forecasts specific to a particular day. Because they know that there's temporal uncertainty from the ensemble prediction systems at that lead time. So what they tend to do, even before they use tools like Decider, they are, in their own minds, they are putting a time window around the NWP output that they're looking at. So this reflects how they are using the weather pattern forecasting tool.
I have a final question. I don't see any more in the chat, but just one final question from me. In the paper, you discuss how the tool is used in earnest by forecasters, and I wonder how closely you worked with the forecasters while you were developing your methodology.
Well, we're very lucky at the Met Office because the scientists, researchers, and meteorologists were all actually in one building. So there's about 1,800 staff at the Met Office, and a lot of them are in Exeter, where the headquarters is. So the operations centre, where all the hydrometeorologists and meteorologists sit, is essentially a designated part of the building. So we're encouraged as scientists to go along to their weather briefs and to listen to what they have to say and to speak with them. So it's very easy to collaborate and design products. And part of setting up the Fluvial Decider product meant creating a prototype. We shared that with them so they could use it in real time, and then they would meet with us regularly, give us feedback, say they like this or they don't like that. And the presentation really evolved a number of times before we ended up with the final version. And we found that some hydrometeorologists preferred the likelihood compared to normal visualization, and others preferred the probability visualization. So in the end, we've included both of those, but I think they work quite well side by side. But yeah, I think to summarize, we're just lucky that we're in the same building, which really helps with that collaboration.
Indeed. Well, thank you very much, Rob. I'm sure everyone's applauding at home, although we can't see and hear everyone. And now I'd like to move us on to our second speaker, who I will introduce now. The second paper is titled Evaluation and Validation of TAMSAT-ALERT, Soil Moisture and WRSI for Use in Drought Anticipatory Action. And our presenter is Dr. Vicky Boult. Her co-authors are Dagmawi Asfaw, Matthew Young, Ross Maidment, Emma Mwangi, Maureen Ambani, Shamton Waruru, George Otieno, Martin Todd, and Emily Black. Vicky is a postdoctoral research associate in the Department of Meteorology at the University of Reading in the UK. Her work has focused on the existence of wildlife in human-dominated landscapes and how anthropogenic changes may impact biodiversity. She works now with the TAMSAT project, which provides operational rainfall products across Africa. Her current role focuses on documenting the impact of TAMSAT research and expanding its use in ecological applications. She is a full-time scientist, but she's also a part-time wildlife artist. And I've actually been to one of her art shows locally with my family, and we all enjoyed her drawings immensely. So, Vicky's paper was accepted on the 29th of September this year, and I'll pass over to Vicky for her presentation. Thank you.
Thank you, Cristina, and thanks, Rob, also for a great presentation. I'd like to just start by saying thank you to the RMetS team for inviting me to give a talk today, and thank you also to my co-authors. I think some of them are listening, but it's a very collaborative project this has been over the past year or so. And as Cristina said, I moved from a background in ecology and conservation to meteorology. So this was certainly a learning curve, and exciting to have my first paper published in METAPS as well. So this paper really is about, it emerged as a result of a collaboration through an existing project with the Kenyan Red Cross. And the Red Cross have been pioneering anticipatory approaches to disaster risk management. So that means rather than responding to disasters when they happen, things like cyclones, droughts, flooding events, we can actually now forecast many of those events, and that opens a window of opportunity in which we can act in anticipation of these events to reduce the impact. So this study really has emerged from that. I'm not going to take you today through all of the results in absolute detail. You can read those in the paper at your own pace, but I'll take you through some of the key results and actually what that means then for application within the humanitarian sector. So to start with, I wanted to just give you this idea of anticipatory disaster risk management. And the Red Cross term this forecast-based action. Now, what that means is traditionally in the humanitarian sector, a disaster would occur. So let's say a cyclone. And as a result of the cyclone, people might be displaced or lose their access to fresh water and food. And in response, the humanitarian organizations would raise an appeal to generate funds to then bring in aid to support people that were suffering. Now, moving to an anticipatory approach means that actually actions are taken before a disaster hits. And the idea with that is that therefore the impacts of the disaster are minimized, lives are saved, livelihoods are saved, and ultimately costs are also saved as a result of acting before rather than after an emergency. Now, there is one problem with that, and that is because forecasts are uncertain. So there's always a risk that a forecast may issue a warning and the weather event doesn't actually occur, or a forecast doesn't issue a warning and the weather event does occur. So it's important to understand how skillful our weather forecasts are for these extreme weather events to understand what action should be taken and when. And that's been the focus of this study. So in the TAMSAT group at the University of Reading, the team have been developing for years TAMSAT-ALERT soil moisture and WRSI forecasting tools. Now, I will tell you a bit more about what TAMSAT-ALERT is in a moment, but just to give you an idea here, like some of the important things we need to know when we're working towards a forecast-based action approach is firstly whether the forecasts that we're using actually relate to the impacts of an event. And in this case, we're focusing on drought. And we also need to know how far in advance those forecasts can give us a reliable warning of that event coming. So that determines how long we have to act before the event comes. So just to introduce you to the TAMSAT-ALERT tool. So TAMSAT-ALERT it incorporates a land surface model, and that land surface model is driven by meteorological variables such as rainfall, radiation, temperature, and wind. Those variables drive the land surface model, and from that we can get an estimate of land surface conditions. So land surface conditions such as soil moisture, and the WRSI, which is the Water Resource Satisfaction Index. It basically describes how much water a crop needs and how much it has available to it. For the rest of the talk, I'm just going to focus on the soil moisture aspect of the paper. If you want results on WRSI, you can have a look at the paper itself, and I'll provide the link to that again at the end of the talk. So what you can see here is a bit of an overview of the TAMSAT-ALERT model. You can see at the top, the blue boxes show the meteorological variables feeding in to the land surface model in green. The land surface model considers things like vegetation type on the land surface and also soil type. And we run the TAMSAT-ALERT model for the historical period, but also for the forecast period. And we combine the two to give us an outlook of what we think the season will look like in terms of soil moisture. Now, the historical period is based on the historical meteorological variables. And the forecast period, we think about what happened in terms of meteorological variation in previous years. And then we can use each of those previous years to drive the land surface model forward and to come up with an ensemble forecast of soil moisture or other land surface conditions. So if we have 38 years of historical data, we will have 38 possible weather futures and 38 ensemble members in our soil moisture forecast. The soil moisture forecast gives a probability of what soil moisture conditions will occur. And we can further weight that ensemble forecast using a meteorological forecast. So for example, if we have a rainfall forecast saying there's an increased likelihood of dry conditions this year or low rainfall, we can preferentially weight those soil moisture ensembles, which are suggesting low soil moisture conditions or dry conditions as well. And ultimately what TAMSAT-ALERT gives us is the likelihood of a drought occurring in this case. So in this study, we focused on Kenya. Now, Kenya is this sort of sweet spot for forecast reliability. There are two seasons in Kenya. The short rains are October, November, December, and the long rains are March, April, May. And you can see that from these plots here, the top plot just shows you the distribution of rainfall throughout the year. And at the bottom, it shows on the left, the percentage of rainfall that occurs in March, April, May, and in the middle, October, November, December, and then the total rainfall on the right-hand side map there. And you can see that the western regions of Kenya are much wetter than the north and the east. But both of those rainfall seasons are important for crop and pasture production, and ultimately, therefore, for food security of the Kenyan population. And that's really why the Kenyan Red Cross are interested in our ability to represent crop growth and pasture growth with the TAMSAT-ALERT soil moisture model. So the first part of the analysis was to understand whether TAMSAT-ALERT provides skillful forecasts of drought. So really the question is, does TAMSAT-ALERT soil moisture relate to drought impacts? So does it relate to pasture availability? And pasture availability is important because it determines livestock production, which again is important for human food security. And we looked at this for the historic period. So we simulated soil moisture from 1983 to 2018, and we compared that against the historic vegetation condition index, which is it's a relative or a normalized measure of the greenness of the Earth's surface, so derived from NDVI. And it gives us, we use this as a proxy for pasture availability or grazing for livestock. And these are just some results from the paper. So this shows on the top the relationship between soil moisture and vegetation condition index for the March, April, May season. So these are seasonal means of each of the variables. And again, on the bottom, it's the same again, but it's for the October, November, December season. And you can see that variation in the vegetation condition aligns closely with variation in the soil moisture generated by TAMSAT-ALERT. You can also see from the R values presented in each plot, actually has a stronger correlation between these two variables than the March, April, May season, but both are positive, both are significant, sorry. There are some slight discrepancies in places, and that's really important when we're thinking about triggering action based on forecasts. So for example, if the soil moisture is much higher than the vegetation condition index, we might actually be missing a year in which vegetation condition is low, and soil moisture is suggesting that that wouldn't be the case. Alternatively, if soil moisture is which way around did I do it? If soil moisture is very low, but vegetation condition is still high, we might actually trigger action based on that forecast and actually issue a false alarm. There was no action needed, but we took action based on the forecast. So these are really important things to think about when we're comparing the two, not just that there's a good correlation, but also when we're missing or hitting or issuing false alarms based on the soil moisture time series here. We also considered how this varies spatially. So here you can see on the left column, we've got the soil moisture climatology across Kenya. In the middle, the vegetation condition index, and on the right, the correlation between the two. And the stippling indicates where we have a significant relationship. And you can see for both seasons, March, April, May is along the top, and OND, October, November, December along the bottom. We have good significant correlations across most of the country. Again, it's slightly darker blue, you can see in the plot labeled F, showing that we have a stronger relationship in the October, November, December season compared to March, April, May. The second part of the analysis was really to understand, once we knew that the soil moisture did indeed relate quite nicely to the vegetation condition, we wanted to know how far in advance we could actually forecast soil moisture to give us, a relative forecast of the vegetation condition for the season. So what we did is we generated forecasts at regular intervals throughout the season, every week. And we looked at how well those forecasts compared to the actual observed outcomes at the end of the season. So we were looking for the historic period again and generating hindcasts and comparing them to what we eventually observed. And what we can see from that, so that this just takes a little bit of explaining, this is just showing you for Kenya's October, November, December season this time. Again, if you want March, April, May, you can have a look at the full paper. But here, each point on each of these plots shows when we generated a forecast or a hindcast, and then we compared it to the overall seasonal value for both soil moisture here in blue and the vegetation condition index in green. And you can see, first of all, that the R value, so this is just the correlation between the forecast and the actual observed value, and the ROC score. So this is looking at how well was the TAMSAT-ALERT forecast able to identify conditions where soil moisture or vegetation condition were below their 20th percentile. You can see that both of those increase as the season goes on. So as we get towards the end of the season and we incorporate more monitoring data into our TAMSAT-ALERT forecasts, we gain greater skill in those forecasts. So those forecasts become more reliable, we're more confident in the forecasts that they're giving us. The other thing to note here is that the dashed lines show where we've then weighted those soil moisture ensemble forecasts with the rainfall forecast, like I mentioned earlier. So we weight the ensemble based on the forecast, and we use the ECMWF forecast to weight the ensemble. And you can see that by including that weighting, we actually increase the skill of the forecast early in the season, which means that we have higher skill earlier on, and potentially more certainty then in what's going to happen throughout the season as we go. And that's important because it means we know how much confidence we have in the forecast, and we can therefore take action based on our level of confidence. So they were the key results from the paper, and really the next steps are down to our collaborators at the Red Cross, and we'll be supporting in their process to develop a forecast-based action plan for drought anticipatory action in Kenya. Now, what that plan needs to include is a definition of triggers. So what does the forecast need to be saying before we're going to trigger action? And then we need to identify which actions will be triggered and when, and also identify the source of funds that will fund those actions as well. Now, a lot of that comes from an iterative conversation with our partners at the Red Cross. But in terms of the forecasts, what we can say is that TAMSAT-ALERT forecasts become more skillful as we go through the season. So if you need to trigger actions that need to happen early in the season, you should be careful because we're less certain about those. So you need to think about actions that are less costly, that have less risk associated with them, or a lower cost if we end up having acted in vain. And then as we move through the season, you can start to gain more certainty on our forecasts and use those forecasts then to trigger more costly actions that need a higher level of certainty before they are reasonable to trigger. And the conversation is ongoing. We're working with Kenya Red Cross now on these and hoping to have some draft protocols in place to pilot over the next couple of years. So thank you very much for listening, and thank you again to RMetS for inviting me, and Cristina for inviting me, and I'll pass back to you, Cristina, for any questions you have.
Thank you, Vicky. That was a really great overview. I think this work is really exciting. I'll give people a chance to type into the chat, but maybe I'll take the opportunity to ask my questions. First off, in the paper, I really liked the way that you and your co-authors explored the different relationships with the correlation analysis. And when correlations are low, you still report that in the paper, even if it was not significant and discussed. So a lot of people would say, well, why don't you just report the very significant ones? Can you explain that choice?
Yes, certainly. So I think especially when we're thinking about using forecasts to trigger actions in the humanitarian sector, for example, it's really important to identify when the forecasts maybe are missing events or drought events, or when they're giving an alarm or an alert that a drought event is coming that then doesn't materialize. So identifying those cases where the forecasts are not so able to pick up drought events is also important, because we can learn, therefore, first of all, we can take some learning from that, and why did we miss it, and what aspects of the season, what characteristics of the drought maybe did we miss, and why. But also, like I was saying towards the end there, a low correlation or a poor correlation is not necessarily a reason to not use a forecast in anticipatory action. It's just a reason to think about, actually, this forecast maybe isn't the most suitable for triggering actions in this set of circumstances, but we might trigger low cost actions based on this forecast that we're less certain on. So yes, it might not be a very strong positive correlation, but it could still give you useful information, which you might use in combination with other triggers or other forecasts to still trigger actions that are perhaps less costly if the forecast then ends up being wrong.
Thank you. That's a great answer. We have a first question from the chat from Ryan. Thank you for the wonderful presentation, he says. And is the performance the same regardless of the severity of the drought event?
Okay, that's a good question. So we looked specifically in this case at a 1 in 5 drought event. Now, the reason we did that was based on the needs of our users, the needs of Kenya Red Cross. So they have a mandate to act on 1 in 5 events, drought events, 1 in 5 years, sorry, drought events. So we based our reasoning on that. Now, I think what would happen is if we changed that sort of threshold of droughts that we were identifying is that we'd continue to pick up the very severe drought events, but perhaps when droughts are slightly less severe, it's harder to distinguish those using the soil moisture information. It's not something we've tested, but it's certainly something that maybe we should consider. Yeah, thank you for the question.
I'll move on to the next question from Nick, who also thanks you for the great talk. How variable is the forecast skill across Kenya in each event? Are you able to look at it in more of a regional approach during some seasons?
Yeah, that's a good question. And actually in the paper, we did look at how the skill scores for the forecast vary across the country throughout the season. We do see that there's some areas that we have less skill compared to others. So I don't know if you remember in one of my plots that I showed, I can actually skip back to it, can't I? Let's go here. No. There. Okay, so you can see here on the bottom right plot, you can see the sort of the rainfall total across the country. And in the western counties, we have much wetter conditions compared to the north and the east, which we call the ASAL counties, the arid and semi-arid landscapes. And in those arid and semi-arid landscapes, we have much greater skill in our forecast than we do in those western regions, which are generally a bit wetter. I think that's because in drier regions, we see that vegetation condition or vegetation growth and productivity is more closely tied to soil moisture variation. So when soil moisture is the limiting factor, which it often is in these dry counties, we have a better ability, therefore, to identify years in which soil moisture will limit vegetation production and have more skill, therefore, in predicting drought in those locations. In the western counties, it's less tied to the soil moisture. Vegetation production is less tied to soil moisture. And we see the same thing in the highlands, which are quite wet across Kenya as well. The only other area worth noting is along the coastal Kenya. We had slightly lower skill along coastal Kenya, and I think that's because it's a slightly different type of rainfall along coastal Kenya compared to the rest of the country. And the underlying rainfall data we use to drive the TAMSAT-ALERT model is TAMSAT rainfall data. It's a satellite-based rainfall estimation system, and that's particularly skillful at identifying these big convective systems. And I think along the coast, rainfall is slightly less connected to those big convective systems.
Thanks for the question, Nick. I don't see any other questions coming up in the chat. So I think you're here, probably you can't hear the applause from everyone else. Everyone's applauding, Vicky. Thank you very much. I just want to say thank you to Rob and Vicky for sharing their work and presenting that valuable work in this webinar, which is a new format for us, and also for choosing to publish it in METAPS in the first place. I hope you've been really inspired as readers of METAPS to go and read their paper if you haven't read their papers, or if you've never read a METAPS paper, they'll be more likely to come and peruse METAPS. If you're interested in publishing with us and have any questions, please visit our website, which I'll put in the chat, visit our website first and then get in touch via email. Also get in touch with us if you're interested in reviewing for the journal, reviewing papers. We're always on the lookout for interested reviewers. In addition to thanking Rob and Vicky for those excellent presentations, which you can revisit because this whole webinar has been recorded. If you think of any questions over the next week for them, conferences@rmets.org is the email to send your questions to, and we'll do our very best to make sure that all the questions get back to the authors and everyone gets their questions answered. So there's lots of thanks coming up in the chat. I have a link in the chat now for the journal itself, and I also will put in, Victoria has also put in the additional questions email address. So thank you very much for attending. I hope you enjoyed it, and thanks again to our authors and the RMet SOC. Goodbye, everyone. Have a nice evening.